All right. Welcome back, everyone. Before we get started, I want to apologize that I'll sit here rather than walk around and point to things. I had COVID until last Thursday, and I'm still feeling really down and slow. Don't worry, I tested this morning again when I wasn't feeling well, so I'm negative. But if you see me being stuck on something trivial, please just help me out, okay? So let's come back to the topic of galaxy formation. This is a lot of messy astrophysics, but one thing that I hope you'll take away from this is that emission line galaxies are pretty finicky objects. So getting the conditions just right for star formation and sufficient emission line flux requires quite a lot of ingredients. And as surveys get better, these will be the main galaxies that we're dealing with. So some level of understanding of this messy astrophysics will be important in cosmology analysis going forward. After talking about halo formation yesterday, which was neat and fit basically on these blackboards, we then came to what's happening to the gas. So there we've been following how baryons fall into a halo and shock heat to the halo temperature and then successively cool through various channels. And that cool gas then forms stars. And at that point, we also have to think about how star formation then interacts with the reservoir of gas again. Because at that point, of course, we produce more photons that will again inject energy into the gas reservoir. And then also supernova explosions will contribute more reheating and may eject some material from the halo altogether. And then in addition to that, there's also AGN feedback. And this type of feedback is really important to understand, to basically match the galaxy luminosity function and the halo mass function. We had seen that we need some kind of self-regulation both at high mass and at low mass. And here is one of a neat diagram showing basically the tracing of gas and then also the various populations in a given halo. This type of bookkeeping is the basis of any semi-analytic model of galaxy formation, and similarly also in body simulations. So it starts out, of course, with material flowing in initially, starting out in the hot gas phase. Then through cooling, we get to cold gas. That's mostly what we talked about yesterday, and how that moves out to a larger and larger radii, providing more gas, providing more cold gas for stars to form. And at that point, then the evolving stars output energy, mass, and metals into the interstellar medium, which then, of course, also change the cooling function. So at that point, cooling becomes more efficient. We get more cold gas, and various additional feedback channels become more important. In particular, with supernova, then we get winds that redistribute materials, also changing the cooling functions in the outskirt of the halo. And there may be gas accreting both from the hot and cold phase onto supermassive black holes, which then also couples back in terms of so-called AGN feedback. If we put this into hydro simulation, that basically means that now our Euler equations get a source term, which is typically rather poorly understood and also really unresolved in the scale of a typical simulation. So that's what people then often call subgrid modeling, and that includes all these processes like the actual cooling of the gas, star formation, and supermassive black hole formation, and feedback. So basically all of those then get an effective model quite similar to these simple rate equations that I showed you for the semi-analytic models already. And just to show you how much this matters, here we a bunch of different observations shown in the small symbols, starting out with the galaxy luminosity function as a function of galaxy stellar mass for a bunch of different hydro simulations. In black, we have the illustrious TNG, which is a pretty current generation of hydro simulations and current understanding of feedback. Then in red is the fiducial illustrious simulation, which is kind of known to have somewhat a strong AGN feedback. And for illustration, also a simulation without galactic winds, so that is feedback from star formation, shown here in orange. Which shows how that would overproduce low mass galaxies, and similarly also produce way too many just in terms of both luminosity function, in terms of stellar mass, and it also would get the galaxy sizes quite wrong. So clearly these different feedback channels affect a bunch of different properties of the galaxies simply by regulating the conversion of gas into stars. Now for AGN feedback, one of the simplest phenomenological models what could use is saying that, we have accretion rate, and that depends simply on the black hole mass, the fraction of hot gas, and the virial velocity. Basically saying total mass of hot gas, and a fraction of that gets directly accreted. This then basically gets converted into luminosity with some fixed fraction of the accreted energy. And this luminosity then in turn basically couples back to the gas and shuts down cooling. Which means then afterwards we also reduce our infall rate simply because of this regulation. And this was first put into simulations in 2005 with dramatic effects. In this typical scenario of having galaxy mergers that have been studied for a long time, they found that if they merge two gas-rich disk galaxies in a scenario with a black hole and this AGN feedback and without, they get substantially different remnants. And let's look at this in detail here in terms of the star formation rate, where we can of course look at the case with black hole and without, and then the black hole accretion rate and mass of the black hole changing in a bunch of different mergers in the case with feedback. So the one thing that's always clear is that mergers will always lead to talking of the gas and an inflow of gas to the center, followed by a burst of star formation. That's true with and without an AGN. But in the case which you can see in the comparison of the dashed and solid line over here. But if there's a black hole and AGN feedback present, then this feedback will quench star formation, and also then regulate the black hole growth in turn, because there's not much of a reservoir. So you can see here, in the absence of a black hole, star formation would continue. With a black hole, it gets shut down really efficiently. And in turn, you can also see how the black hole accretion rate gets reduced, and the black hole mass basically plateaus after the merger. So in that sense, we then end up with red and dead galaxies, which didn't really happen in simulations before. Now that was the very first proposal for black hole feedback, realizing its enormous importance for galaxy evolution. Since then, a lot of different subgrid recipes have been developed. So starting out with a black hole here at the center, I'm just visualizing how this feedback is realized in a bunch of typical simulations where one of the most common ones is the thermal dump, just releasing that thermal energy close to the black hole. That's implemented in a continuous fashion in Illustris and Horizon AGN. And in some cases, this only happens at high accretion rates. Instead of having this kind of energy dump here, the other somewhat similar option is having a thermal dump in the form of bubbles. So this is a sporadic release of energy into the outer parts of the halo. This is a second basically AGN feedback mode, also called radio mode, that's implemented in Illustris. And there's a number of slight variations across different simulations. Then there's another by hand option implemented in some Mufasa and Nihao variations that affect only the gas on the outskirts. And in addition, there can be what's called black hole driven winds or kinetic kicks that more directly transfer momentum into the surrounding medium. And the particular implementations here can be quite different in terms of at which scale or at which distance this sets in, and whether this is isotropic or in particular rather along a particular axis. So basically, people agree that there's AGN feedback, but how that's then actually realized is quite a variety at the moment, which probably is important. One thing we want to definitely be afraid of here is simulator conformity. If all simulators just converge to the same subgrid model, then we would have a really hard time critiquing that and making meaningful predictions. So variety is good in that sense. Of course, in addition to this particular implementation of how the feedback couples back to the gas, they also need prescriptions for forming the initial supermassive black holes, which again is some kind of ad hoc subgrid physics. So with this small sampling of the variety of AGN feedback implementations, let's have a look what it does. And
ultimately, only one of these models would be correct, or all of them? I mean, is there variety in data such that all these models could be correct in some instances? Or ultimately, there is one correct picture, and
I think
the data would exclude.
I would think that most likely none of them is correct. Because again, there are these effective subgrid prescriptions that try to give us an approximation of what could be happening. But I hope on the next slide and in the future it becomes clear why we want this variety. So if we now first look at what AGN feedback does to the matter distribution, in this case total matter, what you see here is on the left the correlation function, and on the right the power spectrum in different simulations. And what I'm showing here is the ratio between a hydro simulation and a gravity-only simulation run with the exact same initial conditions. So let's stay in configuration space, so in the plot on the left, because if there's something that really happens in a localized way, then it's AGN feedback. And the main thing you can see there that there's reduced or suppressed clustering on small spatial scales. And that is because AGN feedback pushes material out. So that's basically gas and dark matter being displaced to the outskirts of the halo. Of course, that has to go somewhere. we don't lose matter in this case. So that's why you then have a bump or an enhancement of clustering at slightly larger scales. And this family of curves shows you that the different feedback implementations and feedback parameters really result in quite a spread. We're talking here about something of order 10-20% effect on the matter power spectrum on small scales. So that is substantial. And one of the reasons why these types of measurements of the evolved matter power spectrum, say through weak gravitational lensing, will have a very hard time constraining dark matter physics on very nonlinear scales. Then, of course, on the right, I also show this effect on the power spectrum, just because some people are more used to thinking about it that way. But of course, the problem is something that's localized in Fourier space, in configuration space, basically at the scale of a halo, then completely spreads out in Fourier space.
So I should take the envelope of this prediction as the systematic uncertainty or uncertainty.
At the, yeah.
That exceed this uncertainty is excluded.
Well, at that point, we should. Yes. If you find a measurement that cannot be described by any of these simulations, then yes, something is definitely is most likely missing in our simulations. The question of the envelope, of course, is always subjective because different people will make different compilations of simulations. So eventually, we will probably want some way of weighing each simulations by its realism. So that is definitely an interesting question for data analysis that I hope to come back to tomorrow. Yeah? So, sorry, can you say? So different people will have different opinions on that. Based on all the studies that I have done, it seems that baryonic feedback at the end actually has a relatively small impact on current S8 results. And I'm happy to show to put in some plots on that into tomorrow's lecture. Likely at the moment, our model for the nonlinear power spectrum on slightly larger physical scales is more important than baryon feedback. And we can come back to that tomorrow. But yes, this is one type of the astrophysical uncertainties that we will have to deal with in data analysis. Now, I promised you a model for clustering, so we still have to put all these different ingredients together. And for that, I want to review here the halo model. So this is based on the partition of matter into halos, and we assume that all matter is enclosed in some halo. If we then know how halos cluster, which we derived, and if we know the mass distribution around each halo, then we can build a model for the clustering of all matter. And then we can extend that whole thing to galaxies and also other traces. So if we're talking about clustering at a two-point level, then we are left with only two options, given that all matter is partitioned into halos. Our two matter particles, so to say, or two volume elements of matter can either be within the same halo or in two different halos. And at that point, it becomes pretty obvious that this one halo term is determined by the clustering of matter within one halo. That is to say, the radial density profile. And then the two halo term, that is the large scale clustering of halos. So let's put that into equations. In the one halo term, we really have to think about the spatial distribution of matter within the halo. So let's write down our mass profile. And then to get a two-point function, that would be the self-convolution of the density profile in configuration space. So in Fourier space, we then get the Fourier transformed density profile squared, simple product, and then to get the contribution to the total one halo term across all halos, we then still have to integrate this over mass. So here we have mass squared normalized density profile squared. That is just basically proper density profile squared. And then we weigh by the halo mass function to give the appropriate weight to different ranges in halo mass. And of course, at the end, we need to correctly normalize so that we arrive at a power spectrum. Let's just write down that term so that we can later easily incorporate galaxies. I'll leave out the normalization. All right. Now for the two halo term, we have different masses, of course. We can write our halo power spectrum as the bias of the halos of those two masses, which we derived yesterday, times the linear matter power spectrum. And then within the halo model, of course, we should not, in principle, not stop at the linear matter power spectrum. Otherwise, on many scales, we do much worse than what you just derived with Misha in the last lecture. So one could then put in nonlinear corrections accounting for these higher order terms. But I'll not talk about those here. So at that point then, we will have to weigh the halo bias over the mass function. And in principle, of course, there could also be a contribution from the halo profile, because that's, again, only localized in configuration space. It's delocalized in Fourier space. So that's why I do have this factor of the density profile in here. But on very large scales, so low k, you can think of this integral basically as the mean bias of the halo sample. So let's just write our two halo term as average bias squared. Okay, that is at the moment just a prescription for how to calculate things. To make it accurate or perform really bad, that then depends on the ingredients that we choose. That is, we definitely need some prescription for the halo profile, where as long as we're discussing matter, the NFW profile is a good start. But at that point still, we need a prescription for the halo concentration as a function of mass. And that's not unique. Here is just a non-exhaustive list of different fitting functions for the halo concentration in the literature. One problem, of course, is that they do use different definitions of the halo boundary. So if you want to choose one of these and plug it into a halo model code, one needs to make sure that halo bias and halo mass function are defined consistently. But clearly this is one option of basically improving our modeling for the halo concentration as a function of mass, for improving the halo model predictions for the matter power spectrum on small scales. How is defined? The halo profile has basically different slopes on the inner and outer part. And the concentration is related to that break in the power law index. So basically, halo with high. the radial position of the break. So a halo with high concentration would have more mass concentrated in the inner parts and be less dense on the outer part than a halo of the same mass with lower concentration. So here's just an example of what the Fourier transformed halo profile then could look like, showing you this normalized U of M and K is a function of Fourier mode. And well, as we need it to be, it asymptotes to 1 at low K. But you can see that there is a substantial variation in the Fourier transformed halo profile at K of order 1 or so. So on those scales, we definitely should be using a more complicated calculation for the 2 halo term than just simple linear power spectrum times bias squared. And then, of course, the actual and then, of course, we can make it arbitrarily more complicated. So here's just the summary of what the 1 halo and 2 halo term for total matter would look like in configuration space on the left, where the 1 halo term is neatly localized on small scales, and then very spread out in Fourier space on the left. At least in configuration space, we can now easily say, well, this region here is the 1 halo term regime. And if we want to improve that, then we have to improve on our description of the halo profile as a function of mass and the concentration as a function of mass. If we see shortfalls of the halo model on large spatial scales, that means we need to include higher order perturbation theory and higher order biasing, basically implementing the EFT prescription you're deriving with Misha together with then an empirical 1 halo term. But here on scales between about 1 megaparsec to about 10 megaparsec, that's where really in the regime of transition from 1 to 2 halo regime, and that's where it gets messy. So improving the halo model on those scales is very empirical work that often is very slow going. Unfortunately, again, then this insight doesn't translate directly into Fourier space. So this, I think, is a very useful diagnostic for what needs to be improved. Now, as a next step, let's finally put in galaxies, coming back to our topic at hand. And in the context of the halo model, we can do that by, first of all, partitioning our galaxies into central galaxies and satellite galaxies. So if a halo so basically a halo has to form 1 central galaxy, and then everything else is called a satellite. And as a next step, then we can introduce empirical forms for the typically expected number of centroids and satellites as a function of halo mass. And we will also need a prescription for the radial galaxy distribution. And at that point, then we can compute the galaxy power spectrum from the centrals, central cross satellite cross term and satellite term. Now, in the past, this worked great. Here's an example from SDSS data showing angular galaxy clustering for different luminosity threshold samples. So we start out with faint galaxies and move to brighter and brighter galaxies. They are here offset for clarity. In reality, the difference in clustering strength is not quite as big. Importantly here then, on the right-hand side, you can see this halo occupation distribution. That is the typical number of galaxies inferred from this clustering. Let's start with the most massive sample, which is split into a central occupation, showing that this curve here, in the case of luminosity threshold sample, asymptotes to 1. And then once you form the central galaxy, there will be additional contributions. It will also have more and more satellites. And this transition of how rapidly satellites are formed is a strong function of halo mass and luminosity. So for the low luminous samples here, say in blue, basically once they cross a certain mass threshold, boom, they have central in this picture, and then it takes quite some extra mass before they will form their first satellite galaxy.
Sorry, how you define, how you do split, how you do the splitting, how you define,
So for us, this, initially this is mostly an operational thing that we need to do in the modeling, and I will show you why now. Observationally, this is actually difficult because you may end up with, say, a galaxy definition that does not include your central galaxy. In a luminosity threshold sample, you should be fine because typically the central galaxy is the brightest object in the halo, so it will be included in your sample. But if you're only looking at galaxies in a given color or magnitude range, then your central galaxy might not be part of the sample. But so let's rewrite the one halo term of galaxies. I'll leave out the normalization. We'll have our integral over mass. And instead of m squared, now we need the number of galaxy pairs. So that means we have our halo occupation for centrals. So these are now pairs of central and satellite galaxies. Sorry. And then we have the radial density profile of the central galaxy. Radial density profile of the satellite galaxy. Plus, of course, the pairing of two satellites. Sorry, this should be. And then the whole thing weighted by the mass function, of course, by the halo mass function. So importantly, here we have the satellite-satellite pair, central-satellite pair. There is no central-central one halo term because there is only one central. And with that, we are then armed to calculate basically this plot part here of the plot. For the two halo term, it's in this approximation, it's again easy, where we just now have to calculate the mean bias averaged over the halo occupation distribution. So for that, divided by the galaxy number density, which would be this integral here just without the halo bias. So with that, we are then armed to basically redo this SDSS analysis if you have a basic halo model code. Yeah?
Yeah, so if we want to compute the statistical properties of this galaxy power vector, then wouldn't you expect there to be like means around all of these halo rotation density functions? So in such that, for example, n squared satellite does also come with some scatter or something, and every halo of the same mass is the same number of satellite.
Yes, in principle, these will, of course, be distributions. In practice, so far, people are just using some kind of fitting function for the mean. And then you have to assume something, whether they follow Poisson statistics or not, when calculating things like satellite number density squared, or satellite occupation squared. That is something that gets inferred from data analysis. And with that, I think my next slide actually is very useful. So let's come back again. No. No? No, please go ahead.
Okay. Yeah, so I was thought you were going to go to the next slide. I was wondering, like, between this 1 million and 2 million position, how, like, what's the limiting thing you now have for, like the modeling? What's the language you consider? Is it, would it be helpful if
So the 1 to 2 halo transition scales are, I think, always outside the realm of proper perturbative approaches. A lot of it is based on fitting functions calibrated to simulations. And a lot of recent analysis are starting to bypass the need for a halo model altogether. They generate n-body mocks or n-body simulations, identify halos, and then use an HUD to populate those halos and measure the power spectra directly from the simulations. That is something that has only become possible rather recently. And based on that, one can then build emulators. And that's probably the future rather than building ever more complicated modifications for the 1 to 2 halo transition regime. But the popular HM code that is widely used as a nonlinear meta-power spectrum model does include some empirical modifications for the 1 to 2 halo regime. Yeah.
If I go to large, smaller scale, the splitting helps me in the sense that the satellite will contribute more, or with this splitting.
So I mean, this.
Does the splitting helps in understanding? I understand that we have the picture, like we have a central galaxy,
Yeah.
and there are satellites moving in this gravitational potential.
So this becomes important when we include further effects that I will just briefly allude to here. So coming back now to the central person or central object of this class, EAGs. Let's look at what we've learned from DESI so far. First of all, on the top there is the measurement in error bars of the redshift space clustering of ELGs in the DESI 1% sample. And the dashed black line, that would be halo clustering only. So that is basically just a two halo term. And in order now to fit this small scale clustering of ELGs, they realized that they need a bunch of additional ingredients in the HUD modeling. First of all, over here you see the mean HUD inferred in different flavors of HUD modeling, where the solid line here, that's the central occupation, and then the dashed lines are satellite occupations. Because ELGs are color and magnitude is selected, they only live and basically are effectively luminosity bin sample. The galaxy became much brighter. It would automatically basically be an elliptical galaxy. So that means that they have a preferred halo mass of order 10 to the 12. So these ELGs live in filaments, and that's where about well, close to 10% of halos of halo mass 10 to the 12 will host an ELG. But then as halos get more massive, they will host, their central galaxy will be something other than an ELG. So the central occupation drops off. Now that well, the central galaxy may be something different than an ELG, that means we can, at these halo masses, have ELG satellites, and within the sample, at least no central. Simply because the central is outside the sample. That's still our standard HUD so far. But what we're seeing in DESI now is that there's some kind of conformity between satellite and central. So if the central galaxy is an LRG, then the satellites are also more likely to be LRGs, and an ELG central will more likely have ELG satellites. And in order to put in these kinds of correlations that are really related to accretion history and star formation history of the larger region, that's where it becomes useful to separately track centrals and satellites. In order to match the clustering seen in DESI so far, it also appears that the radius satellite distribution needs to extend quite significantly beyond the virial radius. So some of these might be galaxies, might be subhalos that have been accreted by the larger filamentary structure before and then are on their first passage around. But a bunch of this also at the moment is really fitting functions or empirical tweaks to fit the data. So this is not really a predictive model for other statistics. If someone wants to do, say, bispectrum analysis or some other measurement on DESI, they will have to go through this entire process of understanding which aspects of the ELG, AHUD matter, again, from scratch. All right. Are there questions about this part? Then I just want to briefly highlight still that several people in this field are really making sure that the tools for this are easily usable. So there are many software packages, just to name a few, Abacus HUD and Halo tools that implement most of this for you already. So if at some point in your career you get to a point where you have to do HUD modeling, you may, of course, sit down and once compute integrals like this by yourself to get a feel for the ingredients. But if you need a fast code for inference at the end and something that's proper validated, after getting that basic experience, it then probably makes sense to Google a bit what software packages are already available. Okay, if that was messy, now it gets really messy. In the next step, we'll talk about how to go from pixels to power spectra. So that comes in the form of systematics, estimators, and then I'll also, if time permits, talk about covariances. So let's start with the topic of foregrounds, which of course is a theme in all of cosmology. And this is particularly rich for spectroscopic surveys when they rely on target selection. So that means that we've selected galaxies based on color and magnitude cuts from a different data set than our spectroscopic survey. And that means then that our spectroscopic survey inherits some of the systematics of the imaging survey. In general, the idea is that if we start out with some true cosmological number of galaxies, and that propagates through the Milky Way, through the atmosphere, and into our telescope with a given survey strategy, then that true number of galaxies will get modulated by all these various foregrounds, and we will typically observe fewer galaxies than there are cosmologically. This is not an issue of the this is not directly an issue of the limiting magnitude of a survey. What you're seeing here is the limiting magnitude of the targeting data for DESI, and which fraction of sky exceeds that limiting magnitude. And then the vertical lines are the magnitude limits for the LRG, ELG, and quasar selection. So clearly, these selection limits are chosen such that basically most of that very high fraction of the sky has imaging data deeper than the selection cut. That's not the issue. But the problem is that any of these systematics just modulates the observed magnitude and thus promotes galaxies below or demotes galaxies below the selection threshold. In addition, there can be funny effects with CCDs. What you're seeing in the right plot is the density of LRGs around very bright stars in the infrared. Now, obviously, stellar density and galaxy density are uncorrelated. These are very different scales, and this is a spurious signal. What's going on is that the amount of photons here really affects the CCD, and our object detection near to these bright objects is screwed up. And these are the kind of basic effects affecting imaging surveys that we need to be aware of in order to properly analyze photometric data, and analyze even spectroscopic data. Of course, that is really where the expertise of large calibration comes in. And I will focus here in my examples on the recent DESI Year 1 data. Simply because that is the state of the art for targeted spectroscopy. I will be very interested to hear soon how this is going for slit spectroscopy in Euclid, but because I'm not in Euclid, I can't tell you yet. So what you see here is a bunch of potential foreground systematics that people listed that could, in the end, affect galaxy clustering. And the colors show you the spatial variation over the DESI footprint. So for example, here we have the stellar density that gets really high as we get closer to the disk of the Milky Way. This is reddening. And then a bunch of survey properties like the air mass for different pointings, the sky background, seeing, and exposure time. All of those, of course, could affect our probability of saying this, the process of saying this galaxy is above or below the detection threshold. And yes, many of these actually affect the probability of a galaxy being detected. This plot is now organized in a way that you see the mean number of galaxies in a given part of the sky, selected by one of these map properties. So for example, over here, it's just the mean number of galaxies in regions of the sky that have an exposure time of around 70 to 80 seconds. And here are galaxies that live in parts of the sky with an exposure time of 200 seconds. And that's normalized by the in-survey mean averaged basically across all these different exposure times. And here you see a very large variation, for example, on the top left in terms of galaxy density as a function of stellar density. Now, these are faint stars. This is mostly separate from the photometry persistence that I talked about with the very bright infrared stars. The two things that can happen here is that we misidentify stars as galaxies, which primarily happens for quasars, because those are very close to point sources, and that we think that the galaxy is a star. Similarly, reddening, shown in the middle here, has a large impact, again, because that really changes the color of a galaxy, moves it around in our selection diagrams, and we miss them. So that's now quite a library of effects. Here we have 12 different candidates. Of course, in the history of various spectroscopic surveys, people have considered a bunch of other effects as well. The standard approach of dealing with them is to first, of course, think about what could plausibly modify the galaxy density in my given survey. That will depend on which bands of imaging one uses, or whether it's a slitless survey. There will be differences between ground-based surveys, where air mass, of course, is a big consideration. That's not the case in space, but there you have to worry about zodiacal light and such. So start out with a list of potential systematics and make templates for them. So of course, you need a map for each of them. And then the idea is to remove this spurious correlation between galaxy density and template value. And that comes in different flavors. One of the most common approaches at the moment is multilinear regression. So basically, in the case if we have only one systematic, it would be a simple line fit here, so that in our corrected overdensities already look much closer to the global average. That gets, of course, slightly more complicated when there's multiple different systematics at play. And then compared to doing this regression at field level, one can also subtract the template 2-point function, say, from the power spectrum measurement, or project out given modes. These techniques were more popular about 10, 15 years ago. But there was a beautiful paper by Noah Vivadik and Dragan Hutra in 2021 showing that in many cases these different methods are actually equivalent. So let's just take linear or regression at field level now as our go-to method for the sake of this lecture. But many of the things that I'm saying would equally apply to mode projection. Now, of course, if we have a list of 12 or more potential systematics that we want to correct for, one thing that we definitely have to worry about is overfitting. So we will need to understand when to stop, so we don't overfit and really screw up the significance of all this. And just to give you one example of how big this effect can be, here is the angular clustering of galaxies in the dark energy survey. This is a simple magnitude limited survey, where red crosses show you the clustering without any weights, and then in gray after correction. Yep. Obviously here on large spatial scales, this is a huge effect. I should also say that this sample is much more subject to systematics than the DESI galaxies because we go a lot fainter. So this is one of the worst case examples. Now, one of the first things that I said is if you want to mitigate systematics, you need a template. And that sounds easy enough, but then when you drill down one level more, the question is which template? And here I'm just showing an example from a EBOS reanalysis for ELGs and quasars, both using standard regression and a fully connected neural net to do nonlinear corrections. And first, they validated all these different approaches on contaminated mocks, showing that, at least in that setup, these methods perform very well. But in that case, of course, they know which template they used to contaminate the mocks. So this is a bit circular in some sense. The main thing that this type of validation really tests is that if the mocks were contaminated by, say, 15 different systematics, and at the end they choose a subset of those in their regression, what's the residual bias? However, then when they apply this on data, where of course we just have to choose a template in our analysis and don't really know what's the actual cosmological or the actual galactic truth, this really starts to matter. So what you see here is the power spectrum monopole using between pink here and brown dashed, two different templates for the stellar density. which I guess as cosmologists we might think, well, that's something that's really well known. We can just count stars. But no, between using SDSS stars or Gaia stars, there's actually this enormous difference in the power spectrum estimate at low K. So for doing, say, inflation science, this is really important. Yeah? That is just the expected variance on the power spectrum for MOX, where, of course, at low K you have huge cosmic variance. So yes, this is just of order 1.5 cosmic variance, but cosmic variance will shrink if we don't improve our templates. This is a residual systematic that wouldn't change. So that pointed out that which template really matters in the case of stars. Let's briefly look at the recent DESI results, where in the top panel here, they show the significance of individual MOCs, of individual systematics compared to the expectation from MOCs. So importantly, in this case here, they looked at one of these systematics in isolation to understand which ones are top contenders that should be in the regression. And based on that, then they define a subset of systematics that goes into the actual systematic regression. And you see the result here for, I guess, the worst systematics in the bottom panel. So for the quasar sample, some of the strongest effects are the PSF in the Z-band related to the luminosity cut, the reddening, and also the point functions in R and G. You can see then the difference between raw as the dashed line and after correction. And of course, this correction here is in a multidimensional space, typically of order 8 to 10 systematics. This is then just a projection into into each of them. But in summary, after this multidimensional regression, they assign a weight for the imaging systematics to each galaxy in the catalog. And that's then what one has to use in the cosmological analysis. One quantity that I still want to point out here on the topic of the importance of templates is this delta EBV. And that is an alternative for calculating the reddening. Typically, EBV is uses just the famous Schlegel-Fink-Bayerner dust map. But of course, that is again one example of one particular choice of a template that's imprecise. In DESI now, they've also estimated reddening from stellar spectra. So really using their own data to get a new dust map. And that's shown in these plots as delta EBV.
So if I look at this plot, these are a few percent effect. No.
Yeah. Yes, but for precision cosmology,
Compatible with the precision. You're saying that what we measure is systematic dominated.
no, I'm not necessarily saying that. It depends, of course, on the spatial scale. Here, in the case of EBOS, for example, there was substantial systematic uncertainties at very low K. In the DESI paper for the primordial non-causality analysis, there's also extensive plots looking at the impact of these systematics. And then they can be of order half a sigma or so for year one, and will become more important in future years if we don't do improve the systematics marginalization mitigation. But typically these are large-scale spatial variations. This has less of an effect on the power spectrum at say K of 0.1 or so, where most of the constraining power comes from in the EFT analysis. Simply because these things vary on larger spatial scales. To just give you a flavor of these different type of effects, I've got one more example, and that is fiber collisions. Again, affecting spectroscopic surveys that rely on targeting. So you can see here basically different tiles of the DESI survey overlaid on imaging data to show you the positions of galaxies. And then within each of these tiles, that's the input of one focal plane, there's 5,000 fibers. And that means that basically within each fiber, in a given observation, we can only observe one galaxy. So that basically means that within each basically patrol radius corresponding to one fiber, there will be galaxies that are missed, even if they made it into the target selection beforehand using our magnitude and color cuts and are in the sample that we want to observe. We are just not able to observe them all within the first pass. So we will need multiple pass through to get galaxies that are within the patrol radius of one fiber. And that means that we will miss several galaxies and basically miss galaxy pairs that correspond to small perpendicular projected radii. Now, of course, the coordinates here are important. This really, at first, this is an angular separation, but we can, of course, then translate that easily to a perpendicular separation of the two galaxies, where this is a clear-cut situation. We can calculate what our fiber radius is, translate that to a perpendicular separation assuming a cosmology, and we know what's going on. But if we are using the usual Legendre decomposition in terms of just radius and cosine theta, or separation cosine theta, the situation gets more muddled. Let's do the easy case first, though. Measuring just galaxy pairs as a function of r perpendicular, one can then easily quantify what fraction of pairs is lost. And that is substantial in the case of DESI year 1, where there have not been as many past tilings of the same area of the sky. This can be up to 80% for the EAG sample. So that is definitely something that one needs to be careful about in the cosmology analysis. Now let's talk coordinates again. Here you see how beautifully this effect is localized at small r perpendicular. But if we then go to our more common clustering multipoles in terms of the correlation function or the power spectrum, then the fiber collision effect becomes less localized. That is exactly because the r perpendicular does not translate easily to the r mu basis needed for computing multipoles. So you can see that basically the fiber collisions here are quite noticeable and would be a significant bias of our analysis at most scales. So the strategy that DESI then chose to deal with this is to remove all galaxy pairs at small transverse separation. They impose a cut in r perpendicular and then calculate the correlation function and power spectrum only for those galaxies, or only for those galaxy pairs, which means that in addition to the systematics weight that we discussed before, which is just a weight for each galaxy, now each galaxy pair also gets a binary weight 0 or 1, whether it's within the fiber collision radius or not. And that's something what one can then, of course, propagate into the power spectrum or correlation function multiple measurement. And at that point, it works beautifully. But of course, our measurements are now quite modified. So that means that in our modeling of the power spectrum, for example, we now need to include this suppression due to fiber collisions on the theory side. That's basically just a bunch of integrals or matrix multiplications. So it can be done. One just has to be aware of it and sit down and do it. While this is really neat for two-point statistics, this approach does not easily generalize to beyond two-point summary statistics. You can ask Misha, for example, about the headaches that this gives in the bispectrum analysis, I think. And if someone wants to do an analysis of novel statistics like K and N, or say density split statistics, this becomes even more complicated. Because at that point, of course, we also have to think about how the different galaxy samples are interconnected and the priorities. So in that sense, basically, you will really have to think about how ELGs, for example, are affected by quasar or LIGs falling into the radius. Yeah? Yes, but it does not work at finite time. It just becomes computationally very expensive. Yeah? Yes, I mean, in angular space, this is easy. If you have spectroscopic data, why would you restrict yourself to just angular clustering? Yes, but quite a bit of information is typically lost in that. In particular, you don't really get to probe with the type of precision uh, for growth. Sorry, again? I am not sure. There's just so many different parts going on in this that, yeah, I don't remember all the parts of the papers. Okay, so I've just touched, really scratched the surface here. Imaging, systematic, and fiber collisions are probably the two most prominent examples for catalog systematics. There are many more, both of those that have already been tackled by collaborations, and likely also unknown unknowns. So it's really important here to acknowledge the immense work done by these large survey collaborations to get these systematics under control. That's a continuing uphill battle, and quantifying the significance of a systematic effect, maybe a PhD thesis already, and then figuring out how to mitigate it might take a whole working group several years. So this is really where a lot of the effort happens, that then gets at the end buried in one of the methods papers for an analysis. But this requires probably at least as much creativity also as doing theory research, because often there is not really an idea even how to set up the calculation in the beginning. Just know, oh, there's a problem. And basically we will never be done. As the statistical precision gets better, that means that we'll have more and more stringent requirements on systematics and mitigation. And I guess I said that already for the fiber collisions and the bispectrum, but it's really important to keep in mind that the requirements on systematics may differ for different summary statistics and for different science cases. Say because some collaboration decided that their imaging systematics mitigation was good enough for those scales that they were interested in. If someone else then gets really ambitious in their analysis and pushes to ultra large scales, beyond what the collaboration had done before, that may require additional work. So seeing what the collaboration has done is a good starting point, and they will show very clearly why they believe it's good enough for their key papers. But pushing beyond that means that one has to scrutinize each aspect of the systematics modeling again. Let's just continue in the standard picture and say we now have a galaxy catalog that has well-calibrated weights that we can use in our analysis. And we also have a plan for how to deal with other catalog level systematics. So let's just talk through the power spectrum measurement and briefly sketch out how we get covariances for those power spectra, or in general our summary statistics, so that we can then turn those into parameter constraints this afternoon. Okay, so we have a galaxy catalog that contains galaxy positions and weights. So from that we can then define an estimate, a galaxy density field. Nothing exciting. Just summing over basically the different galaxy positions with their respective weights. And then in addition, for clustering measurements, we will also need a random catalog. So we generate just random points that will have exactly the same angular geometry and radial completeness as our actual galaxies. And of course, we similarly have to assign these random points systematic weights based on the actual location in the footprint, using the exact same templates that we used to devise weights for the actual galaxies based on their position and the template values at that precise location. And typically we will want this random catalog to have quite substantially more galaxies objects than the real galaxy catalog to minimize short noise effects that I will not get to today. But so often this is an oversampling of a factor 100 or more. While it may sound like, oh, we just generate some random numbers, generating a random catalog that really reflects especially the radial completeness of your survey is again a major task, and not just the case, oh, I know how to call it a random number generator in Python. But that's again beyond what we can discuss in a bit over an hour. So based on our galaxies and randoms, where we can then do a fairly bread and butter power spectrum estimation. And for that, we can define this so-called Feldman, sorry. I'm completely blanking right now. Thank you. So, Yes. Yes. So based on this famous paper, we can then define a field that schematically is a weighted combination of these two fields. That is galaxies minus randoms at that particular spatial location. Normalized to take out the mean number density, and I will not work through the detailed normalizations here because yeah, that's details one needs to do if you implement this yourself. But I think we can just focus on the key effect here, namely that we now have window data this galaxy and random field are only defined within the survey footprint. And my capital W here is again some weighting that is just chosen such that we minimize the variance at the scale of interest. But based on this setup then, of course, we can do a Fourier transform. And you will notice here that basically this is, of course, the actual galaxy density minus the randoms. So basically just an estimate of our survey geometry. Alpha here is number of galaxies divided by number of randoms. And then we divide by the mean density or some transformed version of it. So this should be proportional to delta G of R times our window. And that means then that our Fourier transform field in the end is proportional to the convolution of the true cosmological density contrast from over all space, modulated then by the survey window. And when we then estimate our power spectrum, then again we end up now with a convolution So we have an estimate for the power spectrum that now unfortunately depends on the survey window. And that is a fairly typical approach. In many cases, often when this k is at a scale of order k of 0.1 or 0.2, then the effect of the window is fairly small, just because the window is on so much larger scales than these small scale fluctuations. But this is becoming increasingly important, especially as we push to lower k and higher precision. So actually accounting for this convolution or finding alternate approaches is becoming more and more important, and something one has to be aware of when modeling power spectra. And well, what I did not list here, there is a short noise term that, again, just for this basic concept, so that you know what, for example, Misha will mean later when he talks about window function deconvolution or deconvolved power spectra. This is how this is happening, simply because we only have galaxies within the survey window. There's alternate approaches, but they don't fit as neatly on a blackboard and require quite a bit of spherical harmonics. So I'm not sure that going through that in detail here would add clarity. Now, this was just a brief sketch of what this looks like in the rest frame for power spectra in redshift space. Of course, this becomes a bit more complicated. And especially when we later on, when people then push that to large scales, one really needs to pay close attention to geometry and wide angle effects. But the basic idea first, and to go to redshift space, is that we again have our FKP field F and do a Fourier transform, including the Legendre decomposition. And S over there is our short noise term that only exists for the monopole. Now, when we do this calculation, of course, we have to at some point choose a geometry and how we define distances. And there one can take different approaches for basically defining the line of sight. One could, for example, define a mean line of sight between the two galaxies, or one could choose one of the two sight lines as the line of sight, or use the angular bisector, where currently, in many cases, this endpoint line of sight is used quite commonly because it makes a lot of the integrals easier. But there's alternatives. So for example, there are windowless quadratic estimators that are becoming more and more widely used, so that one doesn't have to deconvolve a window afterwards. Going in a different direction, if one wants to really study clustering on ultra-large scales, say on opposite sides of the sky, then all these geometric approximations become really poor, and one should probably use a different coordinate basis. So, for example, my group at the moment is preparing for an analysis from the spheric satellite, where we really want to basically go down to L of 2 or 3, so measuring clustering on ultra large scales. And for that, instead of using a standard Fourier basis, we are working in a Fourier Bessel decomposition, basically splitting proper radial modes on radial modes and angular modes on in a spherical geometry, which of course means that, well, it's a lot of math, but same principle. The final ingredient that we will now still need to go along with our power spectrum is a covariance. And again, for clarity, let me just work with unwindowed power spectra here, because since if P is proportional to window squared, then cov P is proportional to window to the fourth, and that's just a whole lot of integrals that, of course, we need to do, but that don't easily hide the physics. So this just means that we are really looking at that's just the definition of a covariance. And then we can, of course, slot in a bunch of densities. So that means we have delta of K1, delta of minus K1, delta of K2, delta of minus K2, minus, of course, they're the same term. All right, you know from the previous lectures how to process this term. We can split this up into the different Wick contractions plus a connected term. Let me just keep track of the connected term here first. And then we, of course, have this contraction, which will just cancel with the separate with the product of the two means. So then we need this one times, of course, the two remaining terms. And all right, so we have here our connected term and then these two products of power spectra, where I will not go through the detailed integrals right now to do the mode counting for you. Let me just state the result in the end. So after actually quite a bit of algebra in this case, we then get the bin average trispectrum. And of course, here the Gaussian term that only contributes when K1 equals K2. That's our standard cosmic variance term, which means that we here then have also a prefactor of the number of actual Fourier modes. K squared delta K, P squared. Okay. So power spectrum squared suppressed by number of modes. That's our standard covariance. And then we have a bin average trispectrum, which if we have a good, which of course we can evaluate easily theoretically. The main question then is, do we trust our trispectrum model or not? And unfortunately, this derivation so far is incomplete. Basically, here we just looked at just the delta contrast again defined in an infinite universe. While in practice, our survey, of course, has and only accounted for the finite survey volume in terms of the mode counting here, but not in terms of its effect on the mean power spectrum or on the actual power spectrum. In practice, there is modes larger than our galaxy survey. So that means then our P of K gets modified to P of K plus the modulation of the power spectrum by some large-scale mode, which is something that one could calculate again, say, within the peak background split and halo model. And at that point, we have two choices. We can either include this in the modeling and explicitly marginalize over large-scale modes, which would add quite a bunch of extra parameters. So instead, we can analytically marginalize and put this term into the covariance. So at that point, we will have our standard Gaussian covariance plus the connected non-Gaussian term here, plus something that looks like and then the variance of the density field over the survey window. That happens by just when you would put this in a Gaussian likelihood and marginalize over delta L analytically, or the distribution of delta L's. Because there are density modes in the universe that are larger than our survey. And that will modulate the power spectrum, similar to how we calculated that the halo abundance changes in an over or under density. Just the same way we have to now account for how these large-scale modes affect the power spectrum. All right, that is something that, of course, is very schematic, but don't worry. The community has worked out the details, and some of us also sat down to implement this in reliable codes. So for the redshift space power spectrum, Jay Wadeka did the heroic work computing these integrals and many more, and turning it into a CovaPT code that one can easily download and modify to survey geometries also other than BOSS. I've spent basically most of my postdoc career doing covariances for angular clustering, galaxy lensing, and galaxy clusters. That's also available as a fairly stable code. So let's not worry about just how to in detail put in these practical complications. Let's just say this is the principle, and other people have worked out the detailed math. If we trust analytical modeling, then I guess at this point we can just download our favorite covariance code, computer covariance, and run. But of course, there's limitations. Some of these quantities here are, I'm almost done, 2 more minutes. Some of these quantities here are in a deeply nonlinear regime, and there can be, for example, enormous uncertainty in modeling the tri-spectrum between weak lensing and galaxies at highly nonlinear scales. So we may at least want to cross-check these analytic calculations. Now, of course, if we have simulations, then we can always estimate our covariance. So. That is just the standard definition of an ensemble variance or covariance. That's something we can easily perform. Of course, at that point, we will need simulations that we trust more than our theoretical calculations. There's just one caveat. While this is an unbiased estimator for the covariance, it is not an unbiased estimator for the inverse covariance. So instead, we will need a correction factor. That depends both on the number of simulations available and the number of data points. And at this point, we could then proceed with our simulation-based covariance without incurring this bias from the finite number of simulations. The problem just is that at this point we realize, oh, this denominator here is really prohibitive. We will need substantially more simulations than we have number of data points. Otherwise, this just blows up, inflating our error bars. And say, if you're thinking about a future LSST or Euclid weak lensing analysis with 10 tomographic bins, that is 50 different tomography combinations, all in a bunch of angular bins, the number of data points will be huge. Yeah?
Just clarifying, the bottom line is the estimator of the inverse covariance, or is the inverse covariance?
So this is an unbiased estimate of the inverse covariance.
And it's proportional to the estimator of the covariance.
Yes, with this correction factor. So while theory covariances have some modeling limitations, doing this the brute force way also runs into easily runs into computational limitations. And that's why many new analysis ideas in the end get stuck at the stage, oh, and now I just need a covariance, which turns out to be a lot of work. And I will stop here for this morning. Thank you. Yeah.
So in principle, there's also possibility to estimate covariance using the data itself.
Yes, I mean there are techniques like bootstrap and jackknife, but those also run into a lot of biases easily. So getting a good jackknife estimate is much harder than it sounds. in particular when you are interested also in large scales. There's extensive literature. Will Percival's group has, for example, done quite a lot of work on it recently. A more classic paper is from Peter Norberg from around 2010 or so, showing how hard it is to get good jackknife estimates. And many of these studies were then based on doing jackknife on mocks, or on basically they only considered some cheap kind of mock, say log normal or such, as a simplest example, where you can generate a large number to really estimate the ensemble covariance easily, and then compare that to jackknife estimates on those mocks where we exactly know what the covariance should be. And for example, in the dark energy survey, we spent the last 2 months trying to get to a point where a jackknife agrees with theory, and it was not a problem on the theory side. I wish there was. I mean, obviously, if your simulation does not agree with the data at the level of the summary statistics, that's a problem. But then going beyond that, to estimate that just because we get the power spectrum right, do we get the tri-spectrum right? That's still a different beast. But of course, you don't need to go the ensemble route to test this. So if you have different options at hand for generating simulations for covariances, for example, you could go and directly measure the tri-spectrum in these different approaches and compare, and try to understand what really are my limitations. That is much cheaper than first estimating the covariance and then trying to understand what's going on. Yeah? Mm-hmm. Yeah. Yes, no. That is, I guess, part of the problem with analytic marginalization. At that point, you really have to trust your prior. Problem is delta long, of course, then might also be, I guess, different Fourier modes. So you might have multiple delta long. Yeah. Yeah. But yes, if you're worried about the 10 sigma fluctuation, then explicit marginalization is the way to go. And that is not just true for delta long, but for any other parameter. There's often a bunch of nuisance parameters where people say, oh, these don't really matter that much, and I have a good prior on them. So then they do the same thing of moving it from the model to the covariance, basically completely relying on the prior that they had put. But that then, of course, removes the chance of testing afterwards whether the posterior agrees with the prior.